It's to determine whether a date is valid in the calendar we all use daily. The user will provide the year, month and day as 3 integers, one for the year, one for the month, and one for the day of the month. But first, some ground rules. We will only consider certain years as valid, a totally arbitrary decision. Next, we will assume that all entries are positive integers, also arbitrary. But we must tell the user of all of the errors in his or her submission. This last constraint is introduced because of my frustration with systems that tell you about a single error, and then when you've corrected it, tell you that there's yet another error, and so on until you've submitted the same data many times. Well, let's start. The question for the first condition is, what year has been input? In shorthand, we'll just represent it like this. And this is its set of alternatives. Whoa! Remember that the number of rules is the product of the number of alternatives for all of the conditions. So if each condition has a large number of alternatives, the number of rules will be astronomical. And remember that we have to examine every rule in detail. So what should we be looking for? A smaller set of alternatives as possible for each of the conditions. In this way we will minimize the number of rules that we will have to deal with. William of Ockham, a 13th century scholar, understood this well and introduced us to the so-called Occam's razor. Plurality ought never be posited without necessity. In more modern terms, if you don't understand how something works, assume the simplest thing that it could be, or plainly, don't make things complicated. Or even more plainly, kiss. And if you don't know what that is a mnemonic for, ask the person sitting next to you. So let's start over. The first condition and its set of alternatives, just 3, before the valid period, during the valid period, and after the valid period. We can treat months in exactly the same way. So we already have 9 rules. How about the day? Well, that depends. It depends on what the month is and whether or not it's a leap year. So just what is a leap year? Ah, yes, we all know that, but which years are leap years? Pope Gregory XIII saw to it that Easter would stop creeping toward winter by fixing the calendar in 1582. The algorithm produced by the Vatican librarian Luigi Lelio made 97 years in each 400-year cycle leap years. The rules are simple. Every year evenly divisible by 400 is a leap year. All the remaining years that are evenly divisible by 4 but not also evenly divisible by 100 are leap years. But let's get back to our problem solving. Some minor but important changes to our sets of alternatives. We'll leave the year alone for now, but we'll change the set of alternatives for the month. It turns out that in order to solve our problem, it is much more useful to collect the months by the number of days in them. The 31-day months, the 30-day months, and of course February, which may have either 28 or 29 days. These insights occurred while drawing and redrawing the decision tables. Each time that we are able to cut down the number of alternatives for a condition, we will be simplifying the solution. So here are some more improvements. By cutting down one set of alternatives from 3 to 2, we reduce the total number of rules by a third. With the months, we have increased the number of rules from 3 to 4, but for a very good reason. And then there are the rest of the conditions: the day, and whether or not it's a leap year. Now, let's build the table. To simplify this exercise, we will only consider the valid years. The other half of the decision table will be very similar. Here we have the month and its 4 alternatives: February, the 30-day months, the 31-day months, and the invalid months. Now we add the days of the month, where other represents the invalid numbers and is context dependent. There are only 2 significantly different situations: when it is February the 29th and when the month is invalid and the day number is 29, 30 or 31. February 29th is the only place where we will be interested in whether or not it is a leap year. So here we have our answers, the valid dates. When it is February 1 through 28 or February 29 in a leap year. When it is a day between 1 and 30 in a 30-day month, and a day between 1 and 31 in a 31-day month. But what about letting the user know everything that is wrong? Well, here is the completed table. Here are all the year errors. Here are all the month errors. Here are all the day errors. And here are all the days that may be errors, but until we have valid input for the year and the month, we can't possibly know. Every conditional action may in itself be complex. We can make a decision table for each of these, each condition and each action, that is. This process is called elaboration. To illustrate this, let's look at how to determine if it is a leap year. Firstly, we want to know if the year is evenly divisible by 400. If it is, then it is a leap year. However, if it is not, then we need to know if it is evenly divisible by 100. If it is, then it definitely is not a leap year. If it is not evenly divisible by 100, then if it is evenly divisible by 4, it is a leap year, and otherwise it is not. Action elaborations may have many actions, but condition elaborations may only have one. In every rule in a condition elaboration, there must be a member of the set of alternatives for that condition, and there must be at least one instance of every alternative. Well, here is the definition of when it is a leap year. Every rule in our elaboration has a yes or no in it, and both yes and no are present.